Alright guys, so the purpose of this video is to talk through a few things that maybe you haven't thought about yet. Things that you know, everything that you need to know, but maybe didn't think about it quite in that way. Alright, so 10 things hopefully that you should know, but maybe didn't even think about. Last minute review. Okay, so first, speeding up versus slowing down. The common misconception that I saw on a lot of your surprise attacks from the evil Interbach was the fact that many of you thought that a positive acceleration means speeding up and a negative acceleration means slowing down. That's not the case. Okay, speeding up means that you are accelerating in the direction of your velocity. And so if you have a positive velocity, okay, so let's say that if you have a positive velocity and a positive acceleration, then yes, that means that you're speeding up, because it means that you're moving in the positive direction and that the acceleration is causing you to accelerate in that direction. Okay, now what about this? If you have a negative velocity and a positive acceleration, that means that you're moving to the left. Your acceleration, however, is to the right. That's going to be pushing against you, which actually means that you're going to be slowing down. So when you work a question like this, which asks when is the particle speeding up and slowing down, you have to look at both velocity and acceleration. Now, I'd like for you to try it. I'm going to pause it just a second, and I'm going to put all the work up here, but then I'll show you kind of how to compare it. So if you want to do it on your own, do it right now. Pause the video. Alright, so I've done the velocity and acceleration here, put them on number lines. Now if we put the two together, so I've got velocity here, and if I put acceleration underneath that, okay, which is positive and negative, then the areas where you have the same sign for velocity and acceleration, that's where it's going to be speeding up. If it's different signs, then it's going to be slowing down. So you'll notice that before 2, it's negative and positive. However, from 2 to 4, they're both positive within that region. So speeding up equals between 2 and 4. And notice that we put the greater than or equal to because anytime we're doing an interval, we have to include the starting point because the next point is automatically faster. Now look, after the 4, you've got a negative and a positive, which means it's not until after 6, so t is greater than or equal to 6, and we're only going up to 8, so up to 8. And so that's also speeding up. These other two sections would then be considered slowing down. All right, we're going to move on. Don't want to stay too long here. So then we got binomial and variance. Now, the reason I'm bringing this up is because you are probably used to seeing a specific equation for standard deviation and variance. You've been using it with the data where you've got your list of data, you've got like 20 things, and you put them into list 1 and list 2 in your table, and then you push the one variable stats and it just pops out the answer for you. Okay, the problem is that's not really going to be helpful if it's a binomial distribution. Right, this one is talking about the probability of obtaining heads on a biased coin is 0.4. The coin is tossed 600 times. So this should be a very heavy clue that it's binomial because you have a coin that is either heads or not heads. And secondly, it's being done multiple times. And so what we're going to do is, first, the mean number of heads, well, that should be easy. You just take 0.4, which is the probability of a head, and multiply it by 600 times, and you get 240 heads. Right? That's actually one of the equations in your formula booklet. If you look at the formula booklet, we got it right here. Probability, where's the binomial? There we go. Sorry, that's not probability. Probability is here. Right? So you got some binomial distribution. Oh, there it is, 5.8. To get the expected value or the mean, you take the number of flips times the probability of it happening, and that's how you get your expected value or the total number expected or mean of heads. Okay, now you'll notice here it gives us another equation for variance, np1 minus p. And so we're going to go back to our equation, our question here. So np1 minus p. So it's asking for standard deviation. What I can do is I can find the variance, which is np times 1 minus p, and you can use that equation that will allow you to find out the standard deviation. Because variance, we know, is the square of standard deviation. You just have to square root it and you get standard deviation. So what we're going to do is just put in n, which is 600, times the probability, which is 0.4, and then multiply by 1 minus p, which would be 0.6. And when you put all those together, you should get an answer for variance. Now, I'm not going to go into this too much further because you can get those numbers, you can punch it in your calculator, you can work it out. But do remember that once you get variance, you need to square root it to get your standard deviation. All right? Now, the last question is, find the probability that the number of heads, sorry, I wrote over that, obtained is less than 1 standard deviation away from the mean. So if we're thinking about our distribution, this is not a normal distribution, so you can't use your equations for normal distribution. But we do know that when we do Pascal's triangle, right, you end up with numbers on the inside and outside, and the numbers in the middle are bigger, right? So you do get a pile up here in the middle, more occurrences here in the middle than on the outsides. Well, so from there we say, okay, 1 standard deviation from the mean. We already found the mean, which would be 240 heads. Now, if we go up 1 standard deviation, well, we found out in II the value of the standard deviation. I guess I'm going to have to do it after all. So 600 times 0.4 times 0.6, so that would be 24 times 6, which is 144. And we square root it, so we get 12. Okay, that's okay. You can punch it into your calculator. 12, so 12 up this way would be 252, and 12 that way would be 238. So now at this point, we want to know the probability that the number of heads is less than 1 standard deviation away from the mean. So I don't want 1 standard deviation away, but I do want anything else that the distance is less than that standard deviation. And so what you're going to have to do is use your binomial CDF. Okay. And we're going to find the probability of having the 252, right? And you can put this into your calculator, so I'm not going to write it down. But we don't want 252. We actually want 251 and down because we want less than 1 standard deviation. 252 is exactly 1 standard deviation. So we're going to go from 251 and down. Okay, so you got 600 trials, 0.4, and then we'll put 251. Okay, and that will give us the area from 251 down below. But we want to subtract off 238 down. Again, 238 needs to be on the section that we don't want. This time, however, we're going to go binomial CDF, and this time I'm going to include the 238. Now the reason for this is because I want the 238 to be part of this area that I subtract off of my 251. And so if you subtract those, you should get the correct answer, which is about 0.66 something. Okay, I don't remember, sorry, what it is, but you get the idea. Once again, the idea is just thinking of different ways to use what we already have, especially this idea of variance, which we haven't talked about before, but it's smack dab in the middle of your equation sheet. Okay? Alongside of that, the symmetricity of Pascal and factorials. On the previous page, we were looking at Pascal's triangle, and we already recognized that the ends are always going to be congruent. They're symmetrical. Now, if you were to write this out, if I went down forever and ever and ever, then the first term would be n0, and then the next term would be n1, and then n2, and so on and so forth. Now at the end, you're going to have n, and you should be comfortable with this notation. If not, then we have other concerns. So you got n minus 1, you got n minus 2. And note that the n's, the ones that are supposed to be the same, are n0 and n minus 1 and n1, n2 and n minus 2. We can make kind of a inference from this that anytime we have n over, sorry, no, we don't need that. So anytime we have n minus r, whatever that is, that's the same thing as nr. Now the terms won't be the same, but the binomial coefficient will be. Okay? You'll notice that the n minus 2 is the same as the n2. It'll be at the same position on your Pascal's triangle. And so I just want you to remember that anytime you have, let's say you got n minus 4, that's the same thing then as n4. That may simplify things for you a little bit when you're dealing with factorials, when you have those equations. You remember you got the equation in your booklet that I wanted to make sure to bring up, just remind you about this. You've got the equation here dealing with the factorials, right here. And so sometimes this will be a little bit easier to work with if you have n3 instead of n minus 3. Okay, either way it should work out fine, but it may be a little bit easier to work with if you have smaller numbers rather than having another variable in there. Okay, so that's that idea. So going back to our slides, next is distance from velocity. Now, I'm not going to work through this question. The only reason I bring this up is because your formula booklet has this equation, and this freaked out some people because they're like, I don't know how to get the absolute value integral. That's right, you don't know how to get the absolute value integral. That's why we didn't talk about it in class. You remember in class we said, okay, if you have your graph for velocity and it passes down below the graph something like this, then you would take your numbers, and let's say this is 1 and 5. Then you would do the integral from 0 to 1 of f of x dx, and then you would have to separate it because this is now negative, but we don't want it to be negative for distance. Distance cannot be negative. So we would say minus the integral from 1 to 5 of f of x dx, right? And then you would then add the integral from 5 to whatever of f of x dx because you're now positive again. Remember, this was important for distance, it was important for speed, it's also important for area. Those things that are scalar numbers that don't have direction, the integral will always take into consideration positives, negatives, direction. And so that's what this is representing. It's saying, well, you really should be doing the integral of the absolute value, which is why we switch this to be negative, because that f of x should be negative, we make it positive, therefore we are doing this. Now, side note, your calculator can deal with the absolute value. That's because your calculator cheats. It doesn't actually do the integral. It just does, it adds up a whole bunch of little rectangles and puts all those rectangles together to get the total area. Okay, so you're welcome to work through this question if you want, but keep in mind this is not something to freak out about. The formula is there, but you should know better. You should know that you're just doing the integral and you have to add up all the positive pieces. Okay? Probability distribution functions. Now, hopefully you remember probability distribution functions or probability density functions. Okay? The thing with these is that the sum of all the probabilities from I equals 1 to n, so the probability of all those, needed to add up to 1. Now, the reason I'm bringing this up is because we always did it for discrete numbers. This was before we knew about integrals. Now that we know about integrals, we don't have to do discrete anymore. Okay, discrete meaning that I had to be 1, 2, 3, 4, up to n. It had to be counting numbers. What I want to bring up here is the fact that you've got f of x equals kx squared times k minus x from 0 to 5, and it states that it's a probability density function. What does that mean? Well, it means that if we sum up everything from 0 to 5 inside of this function, it should give us 1, the sum of the individual probabilities. It's continuous instead of discrete. And so what we really want to do here is we want to do the integral of kx squared k minus x minus 6 from 0 to 5. And we do integral. Remember, the integral is just a big S for sum because you're adding up all the rectangles. You're adding up all the probabilities inside, even though you're adding up probabilities that are infinitely small, but you have an infinite number of probabilities. And so you take the integral of this, and that should then be 1. That's the sum of all these rectangles. They should add up to 1. The 0 elsewhere just means in any place outside of that, the probability is 0. So it's not going to affect it. That's why all 100% have to be here. That's why it adds up to 1. From there, you should be able to solve for k. Just a reminder, you can't take the integral of this the way it is. Easiest way is to distribute that and then take the integral of the pieces individually. Okay, so that would then allow you to find k. Now once you have that, we want to find the expected value. Now once again, if we look back at our wonderful equation packet, because that's what we do when we have absolutely no idea what to do, we go look at our formula packet and you'll see there's a couple of things for expected value. One of them's right here, right, which is the one we used before with the binomial distribution, but this is not necessarily a binomial distribution, so we can't use that, nor do we have a number of repetitions. So what we're going to do is we're going to use the other one, where the expected value is the mean. But what is the mean? Well, it's just x times the probability of x. Okay, and it's all those added together. you may remember that we've done this before, right? When we had tables, right? You would have a table and you'd have the values 1, 2, 3, 4, 5, and then you'd have the probabilities, which are like 0.1, 0.15, 0.2, 0.7, and point whatever you need to get up to the, okay, so it wouldn't actually work. Let's just get rid of this. Yeah, whatever. Okay, so we got whatever we need here. Okay, then you would take the 0.1 times the 1 plus the 0.15 times the 2, and you would just add all those together, right? And that would give you the expected value, what you expect to get. Now, that being the case, that's what's happening with this. You're just adding the value times its probability. It's a weighted average. Now, again, the sum is used for discrete values of x, when x can be specifically 1, 2, 3, 4, 5 counting numbers. In this situation, we're not looking at counting numbers. We're looking at a continuous function. So instead of sigma x probability of x, what we're going to be doing is we're going to be doing the integral. That will add them up of x, probability of x, which is still that, so kx squared times x minus 6 dx. Of course, by now you know what k is because you found it in a, so you can put in the k, make the x cubed, distribute it, and then you should be able to finish off the question. Okay, so just the idea that you can use integrals when the probability distribution function is, well, when it is a probability density function, to show that they add up to 1. Okay, probability number 10 is not too much here. I just wanted to give you a couple of thoughts, a couple of ideas. When you get to a very difficult probability question, you want to consider different things. You want to consider Venn diagrams. Okay, you want to consider that the Venn diagram that you used in part A might not be the same as the Venn diagram that you used for part D. So pay attention to that. Pay attention to what's asking at the end. Is a Venn diagram appropriate? Is a different Venn diagram appropriate? Okay, another thing you can do is go ahead and break out the tree diagrams. A lot of times if we use Venns early on, we forget about the fact that we could use a tree diagram to help us out. Remember that when you go along the branches, you multiply, and that each of the branches should add up to give us the final result. Okay, another thing is you have several formulas, right? The formulas are probably going to be necessary in those question 10s. Now, a lot of times they're going to use two equations together, like this one right here, the combined events, because that always works, and the conditional probability, because that always works. I highly recommend when they give you data, write it in this format, B given A, or A and B, or A or B, right? Use that so that you can compare it to these and figure out what you need. Very often on those question 10s, you'll be using two of these together, or possibly two of the conditional probabilities, just in different situations. Okay, so be aware you're probably going to use more than just one equation. So write down as much as you can to give you the data that you need. All right, the last thing that I want to mention on probability number 10s is the fact that you're probably going to need something with opposites. Like, let's say that I've got a school with boys and girls, okay, and they have to take French and or Spanish, but they have to take at least one. Okay, so let's say that the problem gives me, or is asking for, what's the probability of it being the boys or speaking French. Okay, we have to recognize that this, boys or French, well, what's the opposite of that? Well, if we think of a Venn diagram, right, so we've got this, which is boys. That means anything on the outside here is girls. Okay, and then we've got the French circle right here. Now, if they're not speaking French, then that means that they're speaking Spanish. Okay, so boys or French would be any of this, which means the opposite is everything outside, which is girls and Spanish. And so this is exactly the same, or the opposite, sorry, would be the opposite, 1 minus girls and Spanish. And that's similar to one of the questions that was on a past exam. But the idea is there, looking for opposites and using Venn diagrams, using tree diagrams to help you find a piece of information that you're missing could be very helpful. I can't say much more than that just because there's so many different things that they can do with it. But I can say be aware you might need a new Venn diagram, tree diagram, opposites, all those things, more than one equation will be very helpful to you in that last question. Okay? Something that I want to remind you with respect to sector areas and radii. Okay? A lot of people find the area of the shaded region, just say, oh, I got an equation for that, Mr. Bauer. I got an equation. They go to the equation booklet and they go, where's my equation? Oh, there it is. Area of a sector. Area equals 1/2 theta r squared. And so they do that and they go 1/2 and then they go 60 r squared. Now there's a problem with that. Okay, this is 1/2 theta r squared. Okay, if you do that, you're going to find that your circle has, or your sector has an area that is absolutely huge. I mean, I'm talking about almost up in the thousands, just a big number. When the circle only has a radius of 5. Remember, the area of a circle is pi r squared, which is pi times 25. I mean, 25 pi is the area of the circle. You can't have something that's 100. So your first problem is the fact that you use degrees. You can't use degrees in this formula. Both this and the arc length must be in radians. So then you say, okay, well, I'll just change it to radians. And I go 1/2, and then I go pi over 3 because I know my trig, and 60 is pi over 3. And then I can do this, and there we go. So r squared is 25, and then I got my answer. Okay, well, I've got a problem with that in that the area of a sector, remember, a sector by definition is centered in the focus in the center of your circle. So if you use that formula, you're actually not finding the area of this because that's not really a sector. Your sector is this right here. Now you need to go through some geometry, through some reasoning to be able to figure that out, but you can figure out that angle. Go through whatever method you need. You can cut this in half. That will be helpful, right? Drawing radii is also always a good idea. Drawing the radii from the center to any points on the curve will probably be helpful. Those are all 5. Okay, and if those are all 5, then that means that the opposite angles have to be equal because it's an isosceles triangle. You ended up splitting this in half, so you got 30, 30, right? So you got all this information, which means that this is 120, that's 120, and therefore this is 120. And so you should be able to use that information now to use the 120, which is 2 pi over 3, and that will give you this area. So area sector equals 1/2 2 pi over 3 times 25. And then you get the area of the triangles using your 1/2 AB sine C, which you can do using those triangles, and you should be able to get both of your triangles, add it to your sector, and then you got the area. But remember, radii are super important. I can't count the number of times that people haven't answered a question because they didn't pay attention to the fact that that's the radius. Okay. Secondly, and then moving on, we've got dealing with data. I wanted us to kind of think about these things in a different way. So I've got a data set with a mean, an average of 20, and a standard deviation of 6. So we're going to add 10 to each piece of data. So before, the data was 10, 15, 20, 25, 30. And you can do this. You can make up numbers and it's fine. You add 10 to each one. What's going to happen to the mean? Well, the mean is going to be 20 plus 10, because if each value is 10 higher than it was, then your overall average will be 10 higher than it was. So your new mean is 30. The standard deviation, well, that is 6. Standard deviation didn't change. That's the spread. If you add 10 to everything, I'm going to have 20, 25, 30, 35, 40. And the numbers didn't change their spread. They didn't change how far they are from the middle, and so therefore standard deviation is the same. Okay? Now, what if I multiply everything by 10? Well, hopefully you get the new mean if you multiply everything by 10, that it should change the new mean to be 10 times what it was. Now, you can prove all this through use of the formulas, but we're not going to worry too much about that right now. Now, if the new data is being multiplied by 10, that means everything's going to be 10 farther apart, right? This will now be 100 and 150 and 200. Those are definitely farther apart than they were before. They're 10 times farther apart. That means the standard deviation is going to be 6 times 10, which is 60. Now, the variance, of course, is standard deviation squared, which will then be 3600. Okay, these formulas again are found in your equation booklet, which is right down here. And so you got the mean, where you're multiplying this by, or sorry, adding or multiplying by 10. If you multiply, remember, you can just pull it out, put it outside. And then same thing with standard deviation. Standard deviation is, you actually don't have to calculate that by hand anymore, so they didn't give you the equation. But anyway, you should know that if you're multiplying everything by 10, it's going to increase that. Now, if this is on the calculator section of your exam, like I say, you can just make some numbers up. As long as you have a mean of 20 and standard deviation of 6, then it should be fine. If you can't get a standard deviation of 6, then just find out what the standard deviation is. Use your list 1, list 2, one variable statistics, get the standard deviation, and then multiply everything by 10 and see what the standard deviation is, and see if you can figure out the relationship between the two numbers. There's lots of ways to figure these out without knowing if you're not 100% sure of what happens. But it's a good bet that you should be able to reason it through. Okay? Number 2, justifying Maxmin and Inflection. The last thing I want to say on this, and this is just because a lot of people had a hard time, I'm not going to work through the question. If you know that a point is a maximum, like let's say at 3 and at 7 and at 8, we know that we have stationary points. The stationary points, of course, come when the first derivative is 0. Not when x is 0. When the first derivative as a whole is 0, that gives us our stationary points. If you go through and then just finish the sign diagram for the first derivative, like plus, minus, minus, plus, right? You just do that. Then you should be able to figure out whether these are maximins or horizontal or inflections. Okay? If you look at this, that's resembling the slope is positive, and then after 3 the slope is negative. Therefore, it's a maximum. Here, you got a negative slope, and then it continues to be negative, right? So you got negative slope, that means it's a horizontal inflection. And here at 8, you had a negative slope and then a positive slope, which means you have a minimum. The lines I'm drawing are the lines for the original function. The signs are describing the slope, which is the derivative. Now, another way to do this is to look at the second derivative. Okay? And when you look at the second derivative, again, you'll find the zeros. Remember, the zeros are going to be the places where you get inflection points. Okay? And when you look at this, you should be able to say, okay, let's do the derivative. If I did the math, let's say I got negative, positive, negative, okay? And so what we're going to do is we're going to say, okay, well, right here at 3, it's negative, okay? And actually, we're going to have to deal with this a little bit more. But anyway, the idea is here, your second derivative is negative. That means concave down. So that means at 3, it should be concave down, which means it had to be a maximum. It can't be a minimum if it's concave down. At 7, you'll notice that it's horizontal and it's changing concavity. And when it changes concavity, that is the justification of an inflection point. Okay? And then you'd have to have something else because obviously at 8, so maybe at 7.5, there's another inflection point and it goes positive again because at 8, it needs to be concave up, which then would prove that 8 is a minimum because it's concave up there. Okay, and so you can use both first and second derivatives to justify minimums, maximums, and inflection points. Okay, the last thing I need to bring up, get enough sleep. According to National Heart, Lung, and Blood Institute, teens should get 9 to 10 hours of sleep every night. After several nights of losing sleep, even just 1 or 2 hours per night, your ability to function suffers as if you haven't slept at all for a day or two. Now, Mythbusters did this. It said they did it with driving, not testing, but you can make the links. They said, compared with cruising around while tipsy, he drank 2 shots of very alcoholic drink. Okay? He did it once after drinking, and then he did it once after not sleeping for a night. He stayed up all night, and he drove 10 times worse having sleep deprivation. I know you're not going to show up to the exam drunk, but it's worse to come not having slept because your brain does not function. It was the same with Carrie. Hers was 3 times more erratic. Okay, so please remember, get enough sleep. It makes sense. It'll make your brain work better. You'll do better on the exam. And that's all.